Okay, let's go ahead and save this file, by the way. And what we're going to do now is we're going to start looking at the same type of calculations, but we're going to do so not with single point flashes, but with multiple point surveys. Okay, and the first calculation we're going to do is, in fact, what we just did a second ago. We're going to look at the precipitation of a solid phase as a function of temperature and pressure. Okay, we're not going to use calcite this time. We're going to use barite. And the reason we're using barite is because it's a well-behaved salt. So let's do this. Start at the top of the stream, at the top level stream, and add a new stream. And we're going to call this survey solubility. So now again, what we're doing is we're transitioning from chapter 2 to chapter 3. It's a natural transition in the manual and also in the course, because all we're doing now is the same type of calculation approach we used a minute ago, but we're going to do so using multiple points. And what we're going to do first is we're going to keep the units the same. We're not going to burden us down with changing units for now. Okay, we're just going to keep units as just moles, so we don't have to think about it. But we're going to add barium sulfate, BaSO4, to our inflow grid. And by the way, we'll do other salts too after we do this one. Okay. And we're not going to give it any concentration. We're going to leave it blank there. Now I said we're going to do a survey calculation, but I first want to start with a single point so I can make the point more clear. Let's add a single point calculation to it, and then change the calculation type from isothermal to precipitation point. So what we're going to do first is we're going to calculate the solubility of barite at 25 C and 1 atmosphere. And then we're going to add a survey calculation and look at the solubility of barite from 0 degrees Celsius to 100 degrees Celsius. Okay. All right, just like before, once you change it from isothermal to something else, there's going to be some sort of calculation parameter window here, and we already saw this. I didn't point this out before, but you'll notice that the calculation button is red, and that's simply because you'll notice there's some errors here. There's still some things that we have to set up. We haven't selected a target solid. We haven't selected anything to adjust. So you're going to go here, precipitant, and you're going to tell the software to precipitate out barite, BaSO4. And then you're going to adjust barium sulfate. Now, what's the difference between these two? This here is a molecular flow. This is a molecular flow. That's a molecular flow. That is a physical solid. So everything we've done up to this point, when we add components to our grid, these are what we call molecular flows. They don't assume any phase, any phase for it. Calcium chloride doesn't assume it's a solid phase. We only know if it's a solid or dissolved after we do the calculation. We add H2O here, molecular flow. That we don't know if that's going to be ice, a gas, or liquid until after we do the calculation. So that's why we make a point of saying inflows or molecular flows, because these are not physical representations. These are just materials that we're adding without knowing what their final state is going to be. It's an important point to recognize about OLI software. Molecular flows are not specific phases. Even sometimes you'd say, I want to add barium sulfate. I want to add salt to water, sodium chloride. Of course, it's a solid, but the software doesn't realize that until after the calculation. Okay, so here it is. Back to the single point 5, or single point. I add a precipitation point calculation. Barite is being precipitated. Barium sulfate inflow is being added. The initial guess is 0. Press the calculate button, and you're going to see a very small number here. 1.138 e to the minus 5. That's how insoluble it is. So barium sulfate weighs about 237 grams per mole. Okay, 234 grams per mole. And essentially, if you take this number here, we're looking at essentially about, what is that? Maybe 23 parts per billion, something like that, if I did that right. So I'm not even sure. Sorry, if I may have done that math wrong, but essentially that's a small concentration. Okay. No, it's 2.3 parts per billion. It's 2.3 parts per million. There's the answer. 2.3 parts per million.
Hey, AJ.
Yeah. Mm-hmm.
So we're seeing here that the total solubility, as you said, is a little over 10 to the minus 5 mole. And then we go in the phase amounts and we see the solid as
Perfect.
a 10 minus 12.
Yeah.
Could you please elaborate a little bit on that?
That's perfect, because now we can see, we needed to add this much, 2.3 parts per million, but we're only precipitating out that much. This is when you start saying, why are these inconsistencies present? Then you go to the report. And the best place to start is the speciation table. There's a certain amount of material that gets dissolved into the water phase. This is the amount that precipitates out, a very small amount. It's like essentially the first crystallite that forms. Okay. But in order for this small crystallite to form, this is how much has to dissolve into the water in order to get there. So that's case, in this case, that's why. Just like we did with the bubble point calculation, right? The bubble point calculation, the vapor phase is 1 over 10 to the 10th, the total amount, right? When we do a precipitation point calculation, we tell the software to set the amount of solid form to be 10 to the minus 12, essentially a very minute amount, and then add enough material, in this case barium sulfate, to the water until this much solid forms.
Got you. Because we just can't say it's zero. It has to be something really, really small.
That's right. Yeah.
Okay.
And so this is how much dissolves in the water. And once this amount dissolves in the water, this is the amount that precipitates. All right. So we now know that this is essentially the solubility of barite, 1.1 e to the minus 5 at 25C. So now the question is, well, what does it look like over essentially a broader temperature range? That's where the survey comes in handy. So let's go back to the survey, the stream here, labeled survey solubility. And now let's add a survey calculation. This is the first one we're adding, survey calculation. And just to keep things clean, let's just call this BaSO4 versus temperature. Now, when you add a survey calculation, the default settings is a temperature survey. Okay. If you look in the summary, the range is from 25 to 100 degrees C in steps of 5 degrees Celsius. So there are 15 steps, a total of 16 calculations. If you want to change this, you use what's called the specs button. Now, we have two things we want to do here. One, we have to instruct the software that we want to precipitate out barite or do a precipitation point calculation. And two, we have to instruct the software what temperature range we want to look at. So first things first, the calculation type. In the center here, in the center part of the grid, for every survey, you'll always see a calculation type category, a subgrid. Okay. If you were to click on this down arrow here, what you'll notice is you're going to see the same list as you saw with the single point calculation. That means I can do a survey of temperature and pressure, composition, whatever, and I can simultaneously force something else to be constant, like my pH or the solubility. So here I'm going to force my precipitation point to be the same, which means I want barium sulfate to be saturated at every temperature that I test. So first, once I click on precipitation point, you can see two more cells are now opened or become available. Once again, I'll select barium sulfate, or barite rather, as the precipitant and barium sulfate as the adjusting parameter. But now, so that's step number one. Step number two is to change the temperature range. And since we're looking at a broad temperature range for barium sulfate, because in some cases you may have solubilities at 170 degrees Celsius. Those happen in upstream oil production conditions, or even in geothermal wells. We want to study that. What we're going to do is we're going to open up the specs button. So you can see right here, adjacent to the survey by temperature, that was the default one, temperature. Click on the specs button. That opens up a window here. You're going to start the temperature at 0 degrees Celsius. You'll end at 175 Celsius. And you'll go by 5 degrees Celsius increments. So there'll be a total of 35 steps or 36 total points. Now, one of the things I'm debating about internally is, should I make calculation fail or should I tell you upfront what to do? So let me just do this, rather, since we're running out of time. We haven't talked about this pressure yet. That pressure cell there is essentially the confining pressure on our material. Right now, I've got 1 kilogram of water, about a liter of water at ambient conditions. And I've got essentially a plunger sitting on top of that. And it's got a spring on it. And that spring is set right now to create a confining pressure of about 1 atmosphere. If I were to set this to 100, I'm changing the spring load so that now I've got a confining pressure of 100 atmospheres on that. I set it to 50, it's got a 50 atmosphere. At 1, when it's at 1 atmosphere, what that means is, if I go above the bubble point, if I change the temperature of this water so that the partial pressure, the vapor pressure of water exceeds that confining pressure, then I'll evaporate the system. So if I'm going to do a calculation at 175 degrees Celsius, I need to make sure that I have a confining pressure that'll force the liquid to remain a liquid so it doesn't evaporate. Now, I'm not an engineer. I've never memorized the steam tables. I think you guys probably had to, but I'm going to assume somewhere about maybe 30 bar or so is enough to keep the liquid to keep the system as a liquid at 175 C. So we actually did 3 things here. One, we want to know, well, first of all, we want to know what the solubility of barite is versus temperature. So we added a survey to do a temperature survey. We set the calculation to be precipitation point so that the software adds enough barium and sulfate to the water that it reaches saturation. And it's going to do so 36 times between 0 and 175 degrees Celsius. But in order to make sure that the system remains a liquid, I've got to change my confining pressure from my default value of 1 to something that's going to be overburdened. And I'm guessing maybe 30 bar should be enough. Probably wrong, and we'll find out. Once you make those changes, press the calculate button. This calculation will be fast. Okay? I mean, these are very quick calculations. Once you've done that, what I want you to do is go to the plot. Now, all of a sudden, you're going to see a tab called plot across the top there. Okay? And this plot is actually going to plot what we want to see. What I'm talking about is that there's some smart logic in the software, in that if I ask the software to adjust a dependent variable as a function of an independent variable, the software knows that's probably the plot that you want to see. So when you click on the plot tab, what the software is going to show you is the solubility of barium sulfate, or the amount of barium sulfate that had to be added to water in order for the solid to form as a function of temperature. And what we can see, we don't have to get into this, the chemistry of barite, but sure enough, this is an example of a solid phase that essentially becomes more soluble with temperature and then becomes less soluble at higher temperatures. Okay, so it actually is, instead of having just a monotonic curve, it actually has it actually changes. It reaches a maximum, is what I should say. So this is essentially a solubility envelope curve. And you can pretty much do this for, I don't want to say all solids, because some solids cause problems. Okay, but it's an example of how you look at
Almost 10
envelopes.
minutes. Yeah, almost. Thanks, bud.
Okay, was that for us, Dino? Was that, were we talking to somebody else in that case?
So sorry, AJ, somebody stopped by.
Okay, that's it.
I apologize. It has nothing to do with you.
Don't worry about it. Yeah. Okay. So I just want to make sure that there wasn't a question there. But I am going to ask, is there a question in here that you want to ask? Or is there any kind of solid phase that you want to look at in the same way? Okay. Well, let's try something else then. Again, we're sticking with the survey calculation, right? And we're gonna lean on some of the stuff we did before. Okay. So we did a set pH calculation before, and we did essentially phase envelopes before. So the easy one to do next is a phase envelope calculation as a function of composition. What we're going to do now is we're going to take our acetone water phase envelope and ask ourselves, what is the bubble point of a water acetone system as the acetone concentration increases? So let's go ahead and create that one next. It'll be the last one we do for today. Let's add a stream. Right? We're going to call this bubble point BP survey. Actually, survey bubble point. And then we're going to add acetone to the water. But before we do the calculation, since I want to go from pure water to pure acetone, what I want to do is I want to change my units to be mole fraction or mass fraction. Let's do mass fraction. So we have this new stream called survey bubble point. We haven't done anything yet, but now we're going to change our units. But we're going to do so in a simple way. Click on where it says inflows for moles, right there. That brings you right into the units editor. And there, I'm going to have you just do one change. Change this inflow from mole to mass fraction. That'll change the inflows from essentially to mass percent. Now press OK. And now the system is essentially starting out at 100% water, 0% acetone. Next, add another survey. Here, add actually the first survey to this one. Again, everything comes through as you expect, mass percent, water and acetone. And the default setting is survey by temperature. We don't want that. Let's survey by composition. We're going to add acetone to this mixture. So change it from survey by temperature to composition. And then right now you see the calculate button is red. That's because we have to select a component we want to adjust. So now you go into specs. In the specs window, you now see essentially two tabs, a component tab and a range tab. The first thing we need to do is select what material we're going to adjust. In this case, there's only one, it's the acetone. So you're just going to select it. This has got to be colored blue. Right? Now it knows it's selected. Then there's the survey range. And just by convenience, it's already set to be from 0 to 100% acetone. The only thing we're going to do differently is change the increment from 10 to 5. So we're going to have 20 points, or 20 steps, 21 points. You press OK. And once you press OK here, that light's going to turn green. But we're not done yet. Because right now, all the software knows is that we're adjusting acetone from 0 to 100%, but we're doing so at 25 C in 1 atmosphere. What we have to do is tell it, let's do a bubble point calculation. So I'm going to change the composition, but I want to change, but I want to do, when I change the composition, I want to know what the boiling point of the mixture is. So we're going to change the calculation type from isothermal, the default, to bubble point. And we're going to tell the software to calculate the boiling point temperature. Once you do that, you press calculate. This is also a quick calculation. And then you go to your plot. And there what you got is your boiling point curve for the mixture of acetone and water. Okay. Pure water, 100 degrees Celsius. Pure acetone, I don't know what this is, 56 degrees Celsius. And this is essentially the curve in between.
AJ, can we do this in a kind of like a 3D plot? For example, you know, water, hydrocarbon, and let's say H2S.
Like a ternary plot, yeah. Yes, we could because really what we could do here, if I stay with the same story, I could add another composition survey. The only thing we can't do in that case, Adino, is that we can't plot it because we only have a 2D plotting tool. You have to bring this to another tool in order to look at that ternary.
It's okay. It's still very helpful.
Yes, and we can do that calculation on Thursday. Okay, we'll take the H2S, we'll take the hydrocarbon, and then we'll, again, depending upon what surface you want to do, if it's a boiling point curve or something else. Okay, we'll just have to figure out what the independent variable is going to be.
Sure.
So let me tell you now, we're done for the class. We got 3 minutes left. Let me tell you what we're doing next Thursday, or this Thursday rather. We'll continue with chapter 3 and do probably another half dozen types of surveys, so you get an idea of how rich the options are for you. There's a whole lot you can do with it. Whole lot of learning from it. That's what it's always curious. You know, you're always curious about, wow, why is this the case, or what does that surface look like that you just asked about, Dino? And also, you can answer a lot of problems with it too. Okay. Once we get finished with chapter 3. Then we're going to go into chapter 4. It's a must that we do chapter 4. It's when we start adding cations and anions, water analyses. It's a big part of the software. We can't ignore it, even if you only use it on occasionally. And then after chapter 4 is done, the very end of it, we're going to do chapter 5, where we're going to start mixing streams together. Okay. Everything that we've done at this point is that we just calculated the final state of the system. We did no mixing or anything. We just said, these are the settings at the final state. Tell me what is required. How much material, what the final temperature is. But when we go to chapter 5, we're changing that whole idea. We're saying, I've got material A and material B at their initial states. I want to mix them together to make a combined material. What are the changes when I go from this side of the mixer to this side of the mixer? You know, how much heat's released, how much solids form, if a vapor forms, etc. Okay, so now we're going to start thinking more in process. And then we'll be done. And then, of course, we're going to do the redox chemistry before we leave too, since that's important to all of you. Okay, I'm going to send this file out to everybody. I'm actually going to need emails, so I'm going to get with Jim to get those emails, and then we'll send it out to you. Also, there's going to be a video of this course, and so it's available. It'll be available for download once it's compressed or compiled. And then other than that, we'll just see each other. We'll see you guys in 2 days.